So we are going to talk about the diffusion models, and this is the presentation prepared by my collaborators in Romania, Professor Radu, Arnesco, and his students, Alen and Vlad. And as I mentioned, we have the survey paper, which is an archive. So it's kind of material taken from there and some more. So in this lecture, I will talk about motivation, high-level overview, denoising diffusion probabilistic model, which is called for short DDPM, and then noise conditional score model, NCSN, and conditional generation, and then stochastic differential equations, which is called SDE, and then some application and some research directions. So probably it will take 2 lectures, so we'll try to do whatever we can today, then we'll try to finish on Wednesday. Okay, so so motivation. So the diffusion model, I think the first paper appeared in 2015, then there was nothing in 16, 17, 18, then there was something in 1920, then all of a sudden, 21, there were lots of papers, then 22, many papers, and it's continue. So it's a big, jump in number of papers on this topic. So as you have been seeing, that one attraction of diffusion model was that diffusion models can be gains. And as you know that, Jan LeCun and other people have said the gain was a, most prominent creative ideas, in the deep learning generative adversarial network, that you can, generate these images and train the network with this adversarial loss and so on. You have a generator and you have a discriminator. So people are very, very happy with the image synthesis using gains, and many papers and style gains and all those things. But then this very different way to generate images came up with using diffusion model, and that was kind of a big breakthrough. Then there were these conditional generations where you put text as condition, generate that, and there were these papers like Glide, which we'll discuss next Monday, and then DALI 2 and all those things. So also their diffusion model has been used to synthesize images, super resolution, high resolution. Take a small image, resolution, you can generate high resolution images. So so as you have seen, you can put a text like a hedgehog using a calculator. You can generate this very realistic looking picture like a corgi wearing a red bow tie and purple party hat, and transparent sculpture of the duck made out of glass and things like that. So also you can give an image, and then also is image shown here, and then the sentence, then you can put a zebra roaming in the field, generate this kind of image. Okay, so the high-level overview of this diffusion model is, these are the probabilistic model used in image generation. And so we will be hearing a lot about probability distribution and so on. So they involve reversing the process of generally degrading the data. So first we degrade the data, then we, reverse the process and generate the actual sample from the distribution. So there are 2 processes, forward process and the backward process. So forward process, what we do, we have some data distribution like this one, That is, it means all the training samples, they have some distribution, like the training image of ImageNet or some other data set. So then we'll take these images and we'll keep adding noise, and we'll such that this process will end, then that image will become completely noise. We won't be able to see anything. So that noise will have some distribution, and that distribution will be a Gaussian distribution, standard Gaussian distribution or bell curve and so on, as you're familiar with. So now we will go through the reverse process, where we will start with this Gaussian distribution, which is basically white noise, and then remove the noise, and then we'll come up with a sample from original data. And for this, we will train a neural network, and that's where the learning comes in. That will, given a noisy image, it will remove the noise, give you next image, and keep feeding back. We'll get a better image until we get some realistic image, which can be one sample from this distribution. So we go from here to the Gaussian distribution, then Gaussian distribution we go in a way to the original distribution of the training data. Okay, so there are these three categories of diffusion models. One is denoising diffusion probabilistic model, DDPM. Other one is noise condition score network. And third one is stochastic differential equation. And somehow all these are actually related, which is pretty interesting. It's pretty theoretical, nice work and result. And people have been interested in lots of equation, lots of concepts, but at the same time, these things work, which is very nice. Because you can develop the math, very beautiful theorems and lots of proofs and so on. But many times it's not easy to see its application. Maybe it takes a long time. But this is kind of material is pretty impressive that it really works. Okay, so now let's focus on denoising diffusion probabilistic model. So we will start the notation. So we will have the probability distribution. That's a data distribution, and we'll call this P of X0. So it's like the images you have for training images, which has some distribution, and that the data distribution we'll call P of X0, this initial distribution. Okay, and then Gaussian distribution is represented by this N, like a normal distribution, and then that distribution is always of random variable, so that in this case random variable is X, and then mu is a mean vector, and then we have the covariance matrix or a standard deviation. In this case, it's identity matrix, and variance is constant for all the random variables. So this is an n-dimensional vector. X is an n-dimensional vector, which is you can take an image and flatten and make one vector. That's like a X there. So now when we have a distribution, we can sample this distribution, get a particular sample from that distribution, which we call X. And that's the way we are going to do. So we will randomly generate a number Z from normal distribution of mean 0 and identity covariance matrix, and we'll call Z. Then we'll take the mu, the mean of that distribution, we'll add under root sigma multiplied by Z. So that will be a sample from that distribution. That's the way we can generate. Okay. So now the forward process is that we will take a image. So what's happened? Let's try again. Did an animation. Okay. Forward process is that we will take an image Anyway, so we'll take, we'll sample our original distribution, P of x0, and suppose that sample is x0. And then we will keep adding noise to that until it becomes complete noise, and we'll call xt. So we'll do x0, x1, x2, x3, and all this thing. And xt will become a normal distribution with mean 0 and the identity, which means that on the diagonal we have all ones and off diagonal all 0. So that is called forward process. Then we have reverse process. So where we will take the sample from this normal distribution of mean 0 and identity covariance matrix, and we will get xt minus 1, xt minus 2, keep going until we will get x0. So slowly we are able to remove the noise, keep removing noise until it becomes a sample from the original distribution. So those are the two processes, the forward process and the reverse process. Okay. So those are two things. And then now, how do we do this forward process? So what we have, so we want to sample xt. We want to get xt. We are given xt minus 1. We want to get xt. So we have this probability distribution, conditional probability distribution. Given xt minus 1, we want to get xt. And this is normal distribution. So this is the random variable xt. And this is the mean, which is xt minus 1, and this 1 minus beta t. And this is the covariance matrix. So in order to get xt from xt minus 1, this is the process we are going to follow, as is shown here. Okay, so which essentially, we are going to add noise to these things, and noise will come from this Gaussian distribution. Okay, so now we will have this constraint. This beta will be small number, and we will have t goes from 1 to 2, 3, and up to t. So essentially the image is replaced with the noise. We started with this, and this is a process. So now this was an iterative method. So we take x0, from there we get x1, from x1 we get x2, from x2 from x3, and at the end we will get xt from xt minus 1 and up to xt uppercase. So now we can also do in one shot. We don't have to go through all these steps. We can do like this. So we can take x0 and directly we can get xt. And that will again be a normal distribution, which is shown here, of the random variable xt. And this is the mean, x0 multiplied by this. And this is the covariance matrix. So again, that beta hat is defined in terms of alpha, and alpha is defined in terms of beta. So that's the process, which is called the forward process, how we go from x0 to xt directly. Okay, so now we want to look at the properties of this probability distribution. So we talk about that. One is that beta has to be very small. Okay, so with that, we will have this xt will be a normal distribution, gotten this, what we showed earlier. So xt is created from xt minus 1, from here to here, with a small step modeled by beta t. So beta t has to be small. And that's fine. And we are assuming the xt minus 1 comes from region close to xt. Therefore, we can model with the Gaussian. So, which is now from here, we can given xt, we can get xt minus 1. And this process, given xt minus 1, we can get xt. So that's the process, and both are normal distribution. And this one, we have the mean vector and the covariance matrix defined like that, depends on xt. Okay, so now,
Dr. Shaw.
yes.
Dr. Shaw, is it possible to make the PowerPoint a little bit smaller? You can't fully see everything that's in it.
Yeah, so thanks for telling me. So let me do the some problem going on here, right? Okay, so yeah, please, don't put in chat, just unmute and start talking, because I see there are 9 chats, so I don't know what's going on. Yeah, okay, thanks because I like that kind of thing, so people should be able to see here. Okay, so Naveed, you should also be expressive. Let me know if there's a problem. Where we were, I think the way I was sharing the screen, was that a problem? Okay. So we were here. Okay, so let me share the screen again. Now, what's going on? So I will stop sharing, right? I'm not really. Yeah, probably this is all stuck here.
Yeah, Dr. Shaw. So when you have like slideshow, does it show the whole slide, or it is also cutting on your screen?
Yeah, okay. So let's try this thing. Slideshow. Okay. Yeah, I don't know what's going on here. So what should I do? Just okay. Let me try again here. Okay. So open again. I don't know why it's doing this. Okay, so let's try to share again. So I'm going to share this one, not a screen, but just a PowerPoint. So do you guys see now do you see the presentation in the presentation mode?
Yeah.
Yes.
Okay, so let's try. Now you see the whole thing?
Yeah, so far, yes. Yeah.
Okay, good. Yeah, just make noise if you don't see. Okay, so this was clear. And yeah, please don't wait. Just let me know, because I want you to make it clear.
Yeah,
okay.
Dr. Shah.
Yeah,
I was trying to ask what exactly is the covariant matrix in this case, because from my understanding, covariant matrix should be like the variance between some variables, but what are the variables in this case? Is that pixels?
Yes, so this is a vector. See that we have a vector. So we take an image, we flatten it. Suppose it's 100 by 100 image, so it's 10,000 dimensional vector. So the covariance is between each of those elements. And so we will have mean vector, which will be this one. And then covariance will be between each of those.
So all of those variables for the normal distribution is like the is respect to the whole batch.
Yeah, it is a vector value, vector value random variables, right? So you are used to random variable as a one scalar, so which can be like height of the person. But here the random variable is a vector, so therefore when we have a scalar, we just have a standard deviation, one number. Okay, but when we have the vector value, we will have vector, the mean will be a vector, won't be a scalar. And similarly, covariance will be a matrix. Okay.
So each elements of the vector represent an image.
Yes, yes. You take
Okay.
no. Each vector, not the element. Each vector represents an image. We take an image, flatten it, and becomes a vector. So that is one sample from that distribution. Okay.
Okay. Okay. Then the covariance is the variance between different vectors, which means the different
elements of this vector. Different elements.
Okay.
Yeah. Because we have, you can consider there are many random variables in each image, right? There are these different pixels and so on. Okay. Yeah. So you can review the probability, the basic concepts. I won't have time to go in detail, but that's the idea. So when you have like ImageNet data set, so each image sample is a sample, and the random variable is a vector, and we can consider that, take an image, all the values, make one large vector, and that will be one sample from that distribution. So that's the way we do. Okay, so let's continue. So hope we can see this. Now we went through this, and let's look at what happens when the beta t is not small. Then in that case, of course, these examples I'll show you in the one dimension. Suppose the one x is just one scalar, because it's very difficult to draw in multidimension, but the concept is for multidimensional. So here we have again Gaussian distribution, but the beta is not small, so therefore it's much flatter. And in that case, this idea will not work. Okay, so which means we will be less certain where was xt minus 1, because we could have reached xt from many different regions. So because this is a process we are doing gradually, so it's important the beta t should be small. Okay, so now what the idea is that we take the x0 and we want to get in t iteration to xt. So x0 is an image, and it can be considered a big vector, and then we want to keep adding noise until it becomes complete noise, and this will be xt. So now the xt is a pure noise, and we will do these iterations to 2-point t is large. And now we are going to look at what should be the training objective to train a network. But ultimately, we are going to come up with network which will help us to starting from a complete noise to get you the sample. So that's what we want to do. So we go x0 to xt. Now we want to do a reverse process. And the reverse process, as we mentioned, that we will have we want to approximate this process by this neural network, where this will be a normal distribution, again around xt minus 1, which will be our random variable. And then this will have the mean vector, and this will be the covariance. Okay, so these will be approximated by neural network. And that neural network we will call theta is a parameter for neural network, and which will basically estimate the probability distribution p xt minus 1 given xt. So because we are modeling the reverse process, we want to start with a noise, we want to keep removing the noise. At the end, we want to come with a sample. So xt, we will get xt minus 1, xt minus 1 will get xt minus 2, keep going until we get x0. So this is the true process happening. But we will model that by neural network. And as you know, that when we train the neural network, we want to find out the parameters of neural network. And this neural network will model the normal distribution. And normal distribution will have these two parameters, the mean and covariance. And then we want to estimate those from neural network. So that's where the learning comes in.
Dr. Shah, like this mean and variance, are they represented by separate neural networks? So this is like one neural network that is like representing both the mean and variance.
Yeah, we'll good question. So we'll talk about that. Just wait, okay? So so right now it will one network can estimate both, or so we'll talk about it. Just wait. Okay, so now actually, so the question is right here. So the answer is here. So what we can do, so in all these things, one is the theoretical formulation, how we relate these concepts with the statistics and probability theory and so on. Other is how do we actually approximate that using learning. So as you asked the question, so we have now two parameters, the mean, mu theta, and sigma theta. But one simplification we can do that we can fix the variance. Okay, now variance is fixed, and throughout it will be mu, sigma t identity, and we will just estimate only the mean. Okay, so that's one simplification we will do. So now how we are going to train a neural network to estimate these parameters of this distribution. Once we have distribution, then we can sample and we can synthesize images and all these things. So that's a whole process, right? So what we are going to do is choose what is called UNet. And UNet is, in a way, encoder decoder. So we'll take in some image, encode it, and then decode. So it's a special kind of architecture. It's very, very good. So let's say we start with XT, which is a noisy image. And for that, we will also put a T as an input. Because there is XT, XT minus 1, XT minus 2, and X1, X2. So this T is important. So then this neural network will give us output as a mu theta, okay, the mean vector of this distribution. So once we have that, then we basically have distribution because we know the mean and covariance is fixed. Then we can sample this distribution to get XT minus 1. So we input XT to the neural network. It gave us the mean. We put mean here, and then we sample from there. We get XT minus 1. So that will be the process we're going to do. Okay. So now a little bit about UNet. So this network looks like a U, as you see, it's like a U. And this was actually proposed in medical imaging. Actually, the author was computer vision, Thomas Brox. And so input image is actually like an X-ray or, black and white, one channel, and 572 by 572. So we go through this different convolution layer and so on. We end up with the output two channels, output segmentation. One channel will say if this is a cell or this is a tumor. Other channel will say this is not a tumor. So that's the UNet. So we'll go in detail what exactly that means. So in UNet, we will have, this arrow will show 3x3 convolution with ReLU. This one will show copy and crop operation. Then this arrow, red one, will show max pooling. And this will show the up convolution. Max pooling will reduce by 2, X and Y. And here we will upscale, and this will show 1x1 convolution. Okay, so let's look at a little bit more detail. So we start with one channel, and then resolution 572 by 572. Then we will do the 3x3 convolution, and we'll get 570 by 570. And we have 64 channels. Then with another 3x3 convolution, reduced by 568 to 568, 64 channels. So that's one stage. Then we do the max pooling. So from 568 to we'll go to 284. Then convolution and 128 channels, and another convolution. So this become 280. And then from there, another max pooling, 140, 138, 136. And then another max pooling, keep reducing. And at the end, we'll get 32, 30, and 28. Now this kind of finishes the one branch of this U, okay? So now we are going to do upscaling. We'll take 28 to 56, and then we will keep getting this from the left channel, left side, to put it, which is the copy and crop. We'll combine the 512 channels from here and 512 channels from here, and it will become 1024. And then again convolution, another convolution, and then upscale. And then we'll take from here, combine with this. So now from 52 will become 104, then 102, and keep going like that. And these are called escape connections. So at the end, we'll end up with this. So this is the UNet. And it's a very simple network, and actually has a lot of application. And that is used where input is an image and output is some kind of image, okay? Like a semantic segmentation kind of application. As you know, when you want to do classification, you just need a kind of encoder. You need to take an image and get features and then put a classifier. But here, the output is the classification vector of what MLP. But here the input is an image and output is an image. So they used it, so this looks like that. And they use it, okay, one more thing, then I'll show you some results. So, so now what we say that we have the noisy image, XT, and then we get the mean estimation from that. So one thing, we will have to represent the T, which is the time, okay? So now in that one, we can put some fully connected networks and just add them up. So there are different ways to do it. So one way, remember we talk about transformer, how we can do the position encoding using sinusoidal. So that's one possible way to actually encode the time here. Or there's another better way to do is random Fourier features and so on. So there's a lot of details how you put that time with the actual image. Okay, so these are the results they got on the medical imaging images. So the idea is to segment this automatically. Input is this, output this, like that, and it was pretty good in 2015. They got award, and this is also another example on that where they can segment these. So that's a UNet. Now, what we are going to do is to, here the application was input an image, output a segmentation. In our case, input is a noisy image, and output is the the better image, or output can be the sigma value of that particular image. And there are different ways, and we're going to discuss that in detail. Okay, so now we want to train this neural network to be able to do what we want, okay? So now, as you know, in order to train a neural network, which means those, like if you want to do UNet, so UNet has these convolutions, 3x3 convolution, max pooling, and all these are the parameters. So somehow we need to estimate these parameters. And you have learned for image classification, so the parameters, you estimate the loss function is cross entropy, okay? And as I discussed this in the transformer lecture, so the simple notion you have learned in physics is entropy. So entropy is probability multiplied by log of probability. Now, if you look at a little bit more detail, so actually there is this notion of KL divergence. So if you have two probability distribution, P and Q, then we can find the distance between those two. And this is the way we do. So it will be PI divided by PI and log of PI divided by QI. Or since it's a log, so we can do the minus. So PI, log of PI minus log of QI. So, and we can expand this PI log of PI and PI log of QI. So this is the KL divergence. Now, what we do in training the network traditionally, we actually use the one part of the KL divergence, which is this part, PI, QI, which is called cross entropy, okay? So because we want to look at the PI is the distribution of the data, and say QI is a distribution of what network is predicting, so we actually take this loss. That's why cross entropy comes in. So because all these network we are trained, we are assuming a distribution. There's a distribution of network, there's a distribution of the labels, and we want to let the network predict the distribution. We compare with the ground truth, and that's what we minimize the cross entropy. So KL divergence was given by these two mathematicians, and it is important notion. So that's what we are going to use in our training of this denoising diffusion probability model. So this is the training objective, and so this pretty involved. So you want to listen carefully and just be patient about it. So the bottom line is that we want to train a network, and we'll call this network, will give us the P theta probability, and this is theta. Whenever we have theta, which means it's a training, we are training a network, and its parameters are theta. So now the actual distribution is this one, where we are given xt, and we want to estimate xt minus 1. Okay, so which I have been showing you equation. And of course, we have x0, x3, and so on. We go through, and right now we want to do this probability of xt minus 1 given xt, because of reverse process. Now here we have a summation which is from t is equal to t, and then we have this one here, which is when we put that t is equal to 2, so they will become, you will start here to be x1, and this will become 2. So x2 given x1, x1 given x2, then t is equal to 3, this become 3. So x3 given x2, and all this thing, we will have these kind of summation up to t. So now we have these other terms. So here we have x1 to x0, and then we have another term here, which is from x0, probability of xt given x0. So now let's look at a little bit more detail of these terms. So first term, the last term is important because at each time step, p theta, we want to make this as close as possible to this distribution, because this is a network which is estimating, and this what we want to try to do. So we will train network so that the loss function will be like this objective function between two probability distribution. And in order to measure the distance between two probability distribution, we look at KL divergence as I talk about. So this is one probability distribution, another probability distribution. And of course, this is conditioned on the original image, and that's what we have x0. So we start with x0, x1, x2, and so on. So now then we look at this one. So here we know that at the end, xt will be the normal distribution. You want to keep adding noise so that it will become complete noise and it'll be a normal distribution with zero mean and identity covariance matrix. So this, I think we can just ignore because it doesn't depend on theta. So that's on end goal. So that's why we are going to use, this is kind of repeat, yeah, that. And so we now have this as a training objective. And now we want to look at very carefully this. And basically this term. So this is a KL divergence, which means we have two distributions, P and P theta. P theta is for the network, P is this original one. And we want to look at the distance between two distributions. Now we have insisted that these are the Gaussian distribution. Now when they are Gaussian distribution, then KL divergence become very easy. We just have to subtract their means, so which is very nice. So now this term is basically a reconstruction error because we can do this separately. We don't have to worry about that. So we'll come back to that. Just hold on. So now taking this, actually this nice paper, which really made a big difference, they actually simplify this further using this fact that, we have the Gaussian distribution and KL divergence between two Gaussian distribution, just subtraction of mean, and this is what they did. So now we will say that we look at the first P, xt minus 1, given xt and x0, the Gaussian distribution. This is a mean, this is a variance or a covariance. And then the way we generate the mu delta, which is a mean, we generate the sample from the Gaussian distribution with zero mean and identity. And then take the xt and subtract zt from here, and this is the mean. And you can show, there's a lot of derivation, but let's assume that's true. And in this case, we will define we already defined the beta hat, which is in terms of alpha, and alpha is in terms of beta t. And in this case, now we are defining beta delta in terms of beta hat. So then we will have the simplified version of the mu delta, which is the mean of this distribution. Now we will have the mean of our p theta distribution. Oh, sorry, this is not easy. Okay, so that instead of the zt, we will have z theta, which will be the estimation, will be output of our neural network. So now we have two means of this distribution, and we can subtract them, and that will give us a KL divergence. And you can take these and like this. And so what boils down to, we have a zt, which is actually a sample from normal distribution, mean 0, and covariance is identity matrix. And this is the estimation from the network. So network is estimating the noise. And we want to learn the weights of a new network such that this loss is minimized. The noise we put in and what it gives us, is similar. And of course, it is function of time. Zt is should be equal to z theta xt, because we take an image, we put a noise to that, and then we put in network, and then it will give us these parameters. So that's the way it works. So now this is a constant. We can ignore that because there's no learning there. So therefore, now the training algorithm very simple. So we just minimize this. Now, as you see, that we are going to do these different steps of time. We'll go through from t is equal to 1 to uppercase T. We will sample the image from the training data, and we'll sample the noise from the Gaussian distribution, and we'll do this minimize. We'll train your network so that this loss function is minimized. And this loss is called L simple. And so training algorithm then is very simple. So we'll take a sample from our training data, which is called X0, and we will sample from uniform distribution time T, and we will sample the noise ZT from normal distribution, mean 0, and covariance identity. Then we will get XT. So this will be our XT. So which means we'll take the X0, we will add noise to that, which will become XT. And we have already defined what is beta hat and so on. So X2 is the initial sample we got, which is a real image. So it'll become XT, and then we will input that to the network, and then it will output something. And this is definition. So then we will take this loss function, differentiate it with respect to network parameter, then update the parameters, keep iterating. So that's the way we are going to train this unit for this DDPM model. It's very simple. At the end, becomes pretty simple. And it's very intuitive, right? Because we have an image, we add noise like this, and we put in through the network. It gave us the estimate, and then we want to learn these parameters so that it's very similar to this one.
Dr. Shah?
Yes.
Beta T, beta T hat. So can you explain a little bit more on that? What is that symbol, T from 1 to?
Yeah, so beta, so we have defined beta T, beta hat, and beta delta. So they are different. At the end, beta is very, very small number. So it will be, very, very less than 1. So it will be a constant which you will input. Okay. So in the previous slides, I talk about that. So it's just a small number between 0 and 1.
I see. So beta T hat is also just a small number because like on the right side, we have this notation. So I couldn't understand what this is.
This is the beta T hat, because see, there are different things going on. So we have beta, maybe let me go through that. Okay, so let's get out of this. Okay, maybe here. Okay, so we started here. Okay, so you remember that we have, maybe even let's go here. Here. Okay, so beta T is a small number, and we take the T from 1, 2, 3, 4, whatever, up to uppercase T. It's a very small number, smaller than 1. Is that clear?
Yes, yes.
So that's
So,
one thing. So then we have defined, that's the thing with, these notations, so you have to look at that again. So then we define the, let's see here. Then we define the alpha t, which is 1 minus beta t. Okay?
Okay.
Do you see this one?
yes, yes.
We'll see. Okay. So so that's second thing. So then beta t hat is a product of alphas, alpha 1, alpha 2, and so on.
It's a product. Okay.
Yeah, it's all, all these defined. But right now, don't worry about it. Just understand the beta t is a small number between less than 1. So, and that will be given to as a parameters. Okay.
Okay. Thank you.
So let's go where we were here. Okay. So let's see, do again here. Okay, can you guys see the slide presentation mode?
Yeah, we can see that. Yeah.
Okay, good. So that's the algorithm. It's very simple. Then that's it. So we have a unit. We input an image, xt, and I tell you how to get xt from x0. And then this will become the noisy, this network output z theta. And then we'll pass a current noise image along with a t to the neural network. When the result will be z theta, which will be an image, which network will predict at time t. And then we will compute the, this will basically become that we will, from there, we will get a z theta, and z theta is part of the mean vector. And then we have fixed covariance matrix, and we can sample from that distribution the sample xt minus 1 for the next iteration. It may look like that. So the whole thing is that once this network is trained, then we start from the noise. It will x uppercase T will get the next less noisy, you keep going that at the end, we will come up with the actual sample from the image. So that is what the denoising diffusion probabilistic model is.